Okay, welcome back to part two of the considerations when developing the winter forecast, what we look at spot on weather. We just left off on part one with the Madden-Julian oscillation for December, January, and February, the different phases and how they relate to temperature and precipitation, whether it's above normal or below normal in the temperature and precipitation categories. Now we'll move in and talk about La Nina. I'm not going to throw El Nino into this discussion because simply it does not apply this winter. That was an application that we had to look at last year with the forecast, but this year we're just going to stick with La Nina. Right now we're currently in a weak La Nina. So during a typical La Nina year, as a consideration, the red arrow represents the Pacific jet stream. The blue arrow here represents the polar front jet stream, okay, and its configurations. And notice with a La Nina, what you typically have is you have cooler than normal conditions in the Gulf of Alaska, into Western Canada, down into the Pacific Northwest and the Northern Plain states. And then you have more dry and warm conditions along the Gulf Coast states in the south and southeast. All right, so you have basically the coldest air remains well north of the United States, pretty much over the upper Midwest, Great Lakes areas, and into Canada. All right, so with La Nina, that's what happens. And I've been talking about this, how La Nina this year just simply is not very strong. And in fact, the latest forecast models have already indicated that the eastern equatorial Pacific waters have cooled to their lowest point already, and they're already on the road to recovery. So we're looking at neutral conditions. La Nina will transition to neutral conditions starting in January, which basically will factor La Nina out of this winter forecast this year. Another consideration we have to look at are blocking patterns. So if we look at blocking patterns, when you get this strong area of high pressure in the vicinity of Greenland, for example, a huge ridge of high pressure, that's denoted by these maroon colors and red colors here. You get those stronger blocks at higher latitudes, especially into Greenland. What that does is it acts as a blocking mechanism. So you'll get these deep troughs over in much colder conditions and stormier conditions, especially if you have a negative phase of the North Atlantic Oscillation, the NAO, in conjunction with this Greenland block. You really can get some below normal temperatures and above normal precipitation over the eastern United States. And the thing is, with the block, it generally does not allow the eastward progression of weather systems in the mid-latitudes to move readily to the east, northeast, and offshore, off the U.S. East Coast. With the block in place, basically things are locked into a certain pattern, and it's usually colder and stormier with troughing over the eastern United States. So we really have to consider blocking patterns and the forecast for those. Another consideration is snow cover. Now this is from the Rutgers Snow Lab, so we appreciate the Rutgers University for this data. The brown areas on this graphic here show areas with snow that are snow covered right now. You can see almost all of Canada, Alaska, Siberia, Asia, a lot of the Asiatic continent. Really impressive snow cover this year. Dr. Judah Cohen had just put out another blog on the AER website. It's really good if you got a few minutes to take a look at it. But a lot of snow cover. It advanced rapidly this fall. And so this consideration with snow cover, what does it mean for our weather in Southeast Virginia? Well, simply, snow cover promotes more ideal radiational cooling because as sunlight strikes snow cover, it generally reflects a lot of the incoming solar radiation. So it's a high reflectivity, or something known as albedo. So any heat that comes in from the sun is simply pushed back out, re-radiated, reflected back out into space. So it's not very effective in promoting any kind of warmer temperatures above snow. Now, in snowpack in general, the models usually do a very poor job for overnight low temperatures, as an example. It's usually much colder over snowpack than it is over bare ground. So what does this do? Snow cover this extensive over Siberia and especially Canada for the United States, that allows colder air masses to grow colder due to this great reflectivity, greater radiational cooling, and that makes air masses colder, and eventually they become more dense. And anything that's more dense is going to tend to want to move from Canada down into the lower 48 of the United States. The next consideration we move on to is the polar vortex strength and placement. I touched upon this one about a week ago in the winter forecast. So generally what we're looking at is the polar vortex. If the polar vortex is strong, the coldest air remains bottled up or confined to the polar regions. Okay. If the polar vortex is weak, then the coldest air plunges into the lower latitudes. And so some of the coldest winters the last 5 years over the eastern United States were a result of the polar vortex positioning itself, getting displaced, a strong blocking high over the top, and a polar vortex getting displaced into the vicinity of eastern Canada or slightly to the west over Hudson Bay. And the circulation around this polar vortex, this huge upper level low, will promote winds to flow counterclockwise around it and bring much colder Arctic air into the lower 48. This is a graphic from AccuWeather back a few years ago. Just shows you what happens if the polar vortex is displaced. Down at the bottom here, we have a couple examples of vortex, the polar vortex, okay? We have a stable vortex, polar vortex, which basically the coldest air resides over the polar areas and it just stays there. Then we have a displaced polar vortex, which if it's displaced, it kind of moves off the poles. And as you can see here by the red area here, that's the displacement of it. And then the split polar vortex, that is when it breaks in a couple different pieces and brings extremely cold air to more than one location across the northern hemisphere during our winter time. So polar vortexes are very important. Their strength. Are they weak? Are they strong? Where are they at the current time? Are they stable? Is it a displaced polar vortex? A split polar vortex? So that's another huge consideration to take into account. And then you have past analog forecasting methods. The charts here for December show you the blue colors represent colder than normal temperatures, the yellow colors warmer than normal, and the white shading here indicates near normal conditions. Okay, so this has to do more so when we talk about analog forecasting methods, the Arctic Oscillation, the North Atlantic Oscillation. We look back at various Decembers, okay, many years in the past, all right, indicated here and then here. And we say, okay, well, does past weather and the correlations with teleconnections, does that actually work in seasonal forecasting? And there's so many different variables that are involved. Sometimes these work well, analog forecasting methods, but a lot of times they don't because no two winters are ever alike exactly. The smallest details will make the greatest differences. So you can never really trust analog forecasting methods completely. You have to look at a lot of the other stuff we've been looking at in developing a winter forecast. These are just guidelines to use basically for example, we have an Arctic oscillation that's negative, positive, a North Atlantic oscillation that's negative and positive, and these are the trends of the temperatures over that period, either below, above, or near normal. So it's just a tool to use for a forecaster. And then moving on to solar cycles. Low sunspot activity usually correlates to colder periods, while higher sunspot activity correlates with warmer periods. And just a slight variance in the amount of solar radiation or irradiance from the sun's surface can play a major role not only in seasonal forecasting, but with the Earth's climate as a whole. Take a look at this chart here. We have sunspot numbers on the vertical axis, and then we have the years in the Earth's history on the bottom, from 1600 to 1850. So, for example, the little Ice Age area, this was known as a Dalton minimum. And this dip here, this black line, indicates your number of sunspots. So you can see a clear decrease in the number of sunspots, and solar activity was much lower. And that coincided with the year around 1812 to 1816 on Earth, where it was a very cold period of time for the Earth's history. Now, look how the sunspot numbers then increase beyond 1850, and notice that with the numbers spiking up, your general temperatures overall get warmer with time. So solar cycles are very important to take a look at, the number of sunspots, for example. So final thoughts. There's a multitude of teleconnections that result in either amplifying or de-amplifying effects on seasonal forecasts. Which effect is strongest or weakest or forecast to be more dominant? Sometimes everything comes together in a winter season. Everything points to one thing, whether it be warmer or colder than normal temperatures. And sometimes everything works together in unison to amplify the effects. Whereas other winters, let's say we have a negative Arctic oscillation and a positive North Atlantic oscillation, or let's say the Madden-Julian oscillation is in a warmer phase for the East Coast. In this case, it's similar to waves on the ocean. You get constructive, it's called constructive interference, or destructive interference rather. So really there's a lot of variables that go along in the seasonal forecasting. We took a look at a lot of them just right now. Additionally, sea surface temperature anomalies, which we looked at, snow cover, the polar vortex positioning and strength, solar cycles, and past analog forecasting methods. All this stuff goes into creating a seasonal forecast. It's not just simply enough to look at one teleconnection, for example, La Nina, and say, well, it's a La Nina winter, so therefore the winter is going to be like this. Again, there's many competing factors within the ocean and the atmosphere interaction that can actually offset each other or amplify each other. And these complicating factors make seasonal weather forecasting extremely difficult. There's a lot to consider here. This is the kind of stuff that we look at on a daily basis in developing our winter seasonal forecast, as well as looking at the jet stream pattern, the long wave pattern up at 30,000 feet. The jet stream will dictate what type of temperatures we get and the type of weather we get, whether we have a ridge of warmer conditions or a trough of colder conditions. Feel free to send us your weather pictures also and comments on our Spot On Weather Facebook, Twitter, and Instagram pages. Subscribe to our Spot On Weather YouTube channel. We love to see pictures. We also love to get some subscribers and followers. So follow us. That's all we've got for now. I hope you enjoyed the presentation. It's 2 parts. Have a great afternoon.